Okay, Assalamualaikum. Today I would like to explain about the example one here, which is example of the DC machine. So we have question here. A 4-pole DC machine has an armature of radius 15 cm and an effective length of 30 cm, right? Then the pole covers 75% of the armature periphery, and the armature winding consists of 35 coils, each coil having 7 turns. The coils are accommodated in 35 slots. Okay, and the average flux density under each pole equal to 0.85 Tesla. And if the armature is lead wound, determine the Ka, determine the Ea at speed of 1000 RPM, determine the current in the coil and also the torque produced in this machine when the current equal to 400 ampere armature current. And last one, determine the power developed by the armature. How much power in this particular machine. All right. So first we're going to find what is the constant Ka. We know the formula for constant Ka. This is a lead wound machine. So because of lead wound, the number of parallel path equal number of P equal to, in this case, 4. So P equal to 4 equal to A, right? So this is how we're going to solve the problem. Now we go to the right. So we know that the A or number of parallel path equal to A equal to P equal to 4, right? And we can find the A first there. Okay, where A equal to Ka equal to Np over pi A. Np is a number, the total number of turns, right? So it's equal to 35. Coil multiplied by 7 turns. So in this machine, we got 245 turns altogether. And then we can find Ka there. So Ka equal to 245 multiplied by 4. And divided by A equal to 4. Divided by pi, we got 78.0. This is a machine constant, Ka, for this particular armature. And then for the second one, we are going to find the AA, which is voltage induced in this machine. So before that, we need to find the cross-section area first, AP. So a cross-section equal to 2 pi r here. The circumference there, 2 pi r multiplied by the length of rotor here. That gives the total area. Divide by 0.75% first, because we know that the cover only 75% effective area, divide by number of pole 4, then you got this number 0.04, which equal to AP. Then we can find flux per pole. So flux per pole equal to A multiplied by B, and B flux density given in this equation 0.85. Then we got the flux per pole, right? And then we can find the induced voltage here, or generated voltage here, equal to K flux speed. K equal to 78.03 multiplied by flux 0.0374 multiplied by the speed. The speed you must change to radian per second. So 1000 RPM must be multiplied by 2 pi divided by 60. Then we got the generated voltage in this machine. It's 305.45, right? So that's the number B. So number C, they give us the total current equal to 400 ampere. So we know that this machine has 4 parallel paths like that. The current IA equal to 400 ampere like that. Then definitely we can find the current in each coil. So we got 4. So 400 by 4, you got 100. So 100 ampere is a coil current there. Okay, and then they ask us to find torque. What is torque developed in this machine? So torque just use formula K flux IA. Ka flux IA. So we know the K, we know the flux already here, and we know the IA, which is 400 amps. Then we can find the torque in the developed by this machine, 1160.8 Newton meter. And last one, they ask us to find the power produced. How much the power produced by this machine? So the power equal to EAIA. We know the IA 400 amps. We know the EA just now 305.45. Then we can find the power easily lah by multiply these two parameter here. Okay, and also we can also work out the power using the formula torque speed. Power torque speed. Just now we calculate torque already. 116.8, 66.8 multiplied by speed in radian per second. Then we can find the power also. So this give the same answer, whether we can use this formula or this formula, got same things. And we found that in this machine, it produces low voltage high current, because the bigger the number of parallel path, the bigger number of the pole, then we got the bigger current produced, but with less voltage. The bigger the parallel path, the bigger the voltage, the lesser the current. I hope you all this very clear for you. Okay, now we move to the next example, next page there. Okay, now they say here, example 2. What happens if the distribution armature in example 1 is wave wound? Repeat part A to D, right, just now. So here I just show you for KA first, find the KA first. So KA equal to NP divided by A. N just now, 35 multiplied by 7 multiplied by 4. All right, divide by pi, but A is equal to 2 now. Why? Because it's a wave winding, wave wound. So we got 2, then we got 156.1 Ka. Then flux equal to, just now from previous example, we got 0.0374. Then we can find AA here. Watt generated in this machine equal to Ka flux speed. Okay, Ka 156.1 multiplied by flux here, multiplied by the speed, 1000 RPM. Multiply 2 pi by 6, you got 1611.11. Why is different from here and here? Because this is a wave machine, wave wound machine, then we found that for wave machine, the machine produces high voltage, which is bigger than this one. Just now we got 300 something, but here is 600 something now, with the low current. So the current here only 200 amperes only. If you have 2 core, that means got 200 ampere, but the voltage very high. So this is the difference between wave wound and LED wound. Okay, so for wave machine, we have high voltage, low current, right? And for the LED machine, we got the high current, low voltage. So that these two main difference between LED and wave winding. Okay, now we go to example 3. So in this example 3, we have LED wound machine with 6 pole. We have this machine have 6 pole, 72 coils on the armature. Each coil contains 12 turns, and they give the flux, which is 0.039 Weber, and the machine spin at this speed 400 RPM. Determine the EA. So basically, example 2, example 3 is similar, but this one we use the LED wound. Again, first find what? Find the KA and P over pi P phi. So we know that because this is a LED wound, the A equal to P equal to 6, right? And then we can find KA there. 72 multiplied by 12 multiplied by 6, that give the divide by pi 6, you got this Ka, and then the flux per pole given by here, then we can find the E there. So E just Ka flux speed. Ka we know, speed change to radian per second here, and the flux given here, then we can find the generated voltage in this machine easily lah. Okay, so this example very straightforward. We go to example 4 briefly. Okay, in this example, they said here, a 12-pole DC generator wave wound armature containing 144 coil of each turn each. Yeah? So in each coil, they got 10 turn each. Okay, the resistance of each turn equal to 0.011 ohm. Okay, the flux per pole is given to 0.05 Weber and is running at 200 RPM. So how much the voltage and how much the torque produced by this machine? Again, we start with the calculate the machine constant Ka and P over P pi. So because this is a wave machine, then A equal to 2. A equal to 2, and in this machine P equal to 12, right? Then find Ka first. So Ka equal to N multiplied by 144 multiplied by 10 multiplied by P, which is 12, divided by pi 2, right? You got this number for Ka. And then the flux per pole is given there, 0.05. And the speed 200 rotation per minute equal to change to radian per second 20.93, right? And then use formula to find E voltage there, which is E equal to K flux speed. So you can easily find the voltage there. Okay, now we're going to find torque. So torque, in order to find torque, you need to find the current first. So we know that the total coil connected in series per path equal to how many coil we have now? We have 144 multiplied by 10. This is a total coil divided by 12 because we have 12 parallel paths. That means each path has the 120 coil, 120 turns, right? So in each path, it has 120 turns of wire or coil. So we know that each coil has 0.01 ohm resistance. So you can multiply 120 multiply 0.01 ohm. We got in each parallel path, the resistor equal to 1.32 ohm. Okay, so we know the voltage already here, which is 2879.5. So you can divide by this resistance. Then we can have the current at each path, which is 218.14. So the total current will be 218.4, 218.14 multiplied by 12. This is the total current which is equal to IA lah. IA, armature current. And the torque can be calculated by K flux IA. So K flux IA, or K flux IA, this is a K. The flux equal to 0.05. IA equal to this number, then you can get the torque produced in this machine. I think this is very clear for you to try to solve some problem here. Okay, next we go to the example 4A there. So in this example 4A, basically this come from our previous test or exam. I not remember, but yeah, it's kind of that. Okay, we have here 8 poles, 25 kilowatt power, and 100 watt DC generator has led one armature, which has 64 coil with 60 turns per coil. So it rated speed equal to 2,400 RPM. Okay. First, how much flux per pole required in order to produce rated voltage in this generator at no load condition? Okay. So how much the flux required there? So we know we are given the voltage already. This is equal to E lah, voltage induced E. Okay. We know the power already. We know the P, and we know the it's lap one machine. So because of lap one, the A equal to number of pole equal to 8. So now first find the what is it? The flux per pole. So what is flux per pole there? Right. So this is how we can solve problem lah. I show you briefly how to solve problem there. So we had the power of 25k, the voltage rated equal to E lah, 120, the speed 240, and find the n number of the total of turns inside the machine, which could equal to 64 multiplied by 16. We got 1024. This is the number of turns, total number of turns in the machine. Okay, and then find the flux per pole. So the flux per pole can be given by this one lah. This one, this formula. Okay, this is basic formula for the generator, right? We know the Ka, Np over pi A, and we know already 1024 there is product of 64 and 16. P equal to A, because it's for lap winding now. A equal to P pi divided by A. So you can cancel each one, then you got this Ka, the constant machine, right? And we know the AA given there, which is 120 A. Then we can find flux there per pole. So just use the formula. So flux equal to E divide. Flux equal to what? E divided by Ka speed. Ka multiplied. But speed need to change to the radian per second. And we can find the flux, which is equal to this number. Okay, that's how we think. Okay, next second one, they ask us to find the where is it? Okay. What is the current in each path? What is the current for each parallel path in the armature for generator at rated load? So they ask us to find the current in each path now. How much the current in each path? Go back here. So we know the power equal to 25 kilowatts. We know the voltage, rated voltage 120. So from there we know the IA equal to P divided by V, just 208.3. This is the total current in the machine. Then we know the P equal to how much just now? P equal to, in this case, 8. P equal to 8. Okay, number of pole equal to 8. So divide lah. So just IA, total current divided by 8. Then you got this current per path. Current, this is current per path. 26. Okay, 0.042. So it answered that question there. They asked us to find the current in each parallel path. So we found all that already. What is the number C? What is the induced torque in this machine at rated load? They asked us to find torque now. Torque equal to what? Just now we know torque equal to K flux IA. Okay, K flux IA. This is formula for torque. Ka we know already just now. How much Ka just now we found right here? Ka equal to here, 3 to 5.949, we know the Ka there. And the flux, we know already, here, 1.465 multiplied 10 to the power negative 3. Then we know the Ia, which is total current just now, which is 208. So by multiply these three terms, then we can find the torque produced, 99.472, or also can be worked out by torque to power divided by speed. You got the same answer. All right, the last part they ask us here is to find the if the resistance of the winding, if the resistance of this winding equal to 0.01 ohm, 0.011 ohm per turns, what is the armature resistance of the machine? They ask us to find the total resistance of the machine, which is represented by Ra. Okay, so what is Ra in this machine? They give us each winding has 0.011 ohm, the resistance. So you need to find the total resistance now. Okay, so basically the machine look like this one. We got 8 paths together like that. So each conductor here or each coil here represent the ohm of 0.01 ohm. This each coil here like that. Alright, so we know that the total conductor equal to just now 10. The total coil equal to the total number of turns 1024, and we have 8 parallel paths. So you divide by this one, divide by 8, you got the number coil in series equal to 128. Okay, so in this series path you got 128 turns altogether. Okay, in each parallel path lah, 128 turns. Okay, and you know that each turn carry 0.01 ohm, so just multiply lah. So 0.01 ohm multiplied by 128, then we got 1.41, 1.408 for each path. So for each path here, every path that got 1.408 ohm. So now we got altogether how many paths? 8 paths. So we can find, in order to find the total resistance, you just divide by A only lah. So 1408 divided by A, then we got the total resistance, which represent the armature resistance of the machine, which is equal to this one. If you look at that part, then the resistance here equal to 0.176. Okay, so that's answer the question. Last question, which is find the RA, armature resistance of the machine. I hope you can follow this exercise here. They're very straightforward, I think. Exercise 4A. I just put new one here lah, just to make sure you get more understanding insight about the calculation of the armature winding. So, okay, this part we have done already before. Magnetization, basically we just want to know the curve. When we run the machine, previously we run the machine, we measure IF with respect to water induced EA, then we can get the plots there lah. This is a plot for the EA versus IF. EA. Okay, when the IF change, EA change. Then this curve represent the relationship between voltage induced and also the field current there. So relationship between these two, we call it the magnetization curve. Okay, so at different speed, we got different curve. The higher the speed with the same IF, we got the higher the voltage. It's simple like that lah. Okay, then next we go to the classification of DC machine. So we know the DC machine can be configured in many ways. By interchanging the winding between between the armature winding and its field winding. Okay, why we do that? Because we want to have different variety or different performance of the machine with respect to VA performance lah. We can have variable kind of performance between voltage produced, terminal voltage, and also IA, load current. So that's one of the characteristic of the machine. Okay, we know machine have two parts. We got what we call it, the field side, field winding, and also we got the armature winding. So the field winding can be excited by two ways lah, by shunt winding or by series field winding. The shunt or series. It can be shunt or can be series. Shunt means we have very large number of turns in that winding. Because of that, the current will be small. No? Normally, it takes about 5% of the rated current. Why? Because of the very high resistance, the current will flow very small. Whereas for the series winding, it has lower turns. That means lower resistance, and definitely it carries big current compared to the shunt winding. Okay. If both winding used, or sometimes we call it the compound machine, the series winding is wound on the top of shunt winding. Then series winding can be at or opposed to shunt winding. So what happens by doing that, we can have different characteristic of the machine, different VA characteristic. Now I show you the some machine there. The first part, you call it the first kind of one, we call it the separately excited machine, where we have two source there. We got source for the field and we got source for the armature. Because of these two different source, that means our field current is supplied separately with the different supply. So that's why we call it the separately excited DC machine. This kind. Number B, we got series winding. In this winding, the series coil, we connected series with the armature. So that's why we call it series machine. It can be generator or motor, doesn't matter lah. It's a series machine. And the third part here, we call it shunt, because we connect shunt winding in parallel. We connect the field winding in parallel with the armature winding. So this kind of machine, we call it the shunt or parallel machine. And the fourth one, we call it the compound machine, where we combine both winding. We have shunt winding, we have series winding together. And the other one is long shunt. How we configure series winding and armature determine whether it becomes short shunt or long shunt. Okay. The first machine here, separately excited machine. The machine not needed the initial flux residual there. If the machine has no residual flux, doesn't matter, it still can work. What is the initial flux? This one here. I mean, at IF0, the machine already magnetized. It has some flux there. For the separate excited machine, it does not this one. Doesn't have this one. It's okay. It's can working. But for the other machine, series, shunt, and compound, in order to make the machine work, it must have the residual flux inside it. You must have this kind of flux, because there is no source that can supply you flux at initial things. So that's why when you start to rotate the machine must contain some flux inside that. That's why they call it a residual flux. So that's why we call this machine is self-excited generator. That's why, because we need whenever you run the machine, the flux is already there. Okay. Okay, this is some kind of waveform lah, the characteristic. When we change the configuration between field winding and armature winding, we can have this kind of characteristic, VA versus IA lah. VA versus IA. You can see here, this shunt. Shunt means when you apply more loading to the machine, the voltage terminal will drop like that. The bigger the current, the bigger the drop. So dia punya voltage regulation not so good. Okay. In separate excited, at no load, this is a no load, call it. This at no load and full load here, the voltage at terminal almost similar, drop very small. So separate excited machine is very good for voltage regulation machine. It can regulate voltage even though at full load, the voltage drop very, very small compared to shunt. Okay. Compound depend whether we have the differential compound, we have the flat compound, over compound, and so on. So the profile can be changed here, but they just draw one of the profile there, like that. And the other machine series. In series machine, you see here, you like the field current equal to armature current. That means the armature current is supply field, is supply the flux to the machine, right? So when IF equal to 0, so there is no voltage induced. Okay, that means there is no flux in the machine. When you increase IF, IA also increase. Then the machine start to develop the voltage. I mean the flux proportional to IA or IF here lah. That's why you can see like that. The bigger the flux, the bigger the IA, the bigger the voltage generated in the machine. That's why you can see the profile like that. See, yeah? So the bigger the IA, the bigger the voltage induced. The bigger the IA, the bigger the voltage. That's the for the series machine. Okay, I hope this very clear explanation. Then you can have some good thing about that. I'm going to the next slide here, just to show you some almost similar, but maybe you can get better understanding. Okay, and this is a good slide also for us, I think. Okay, so just now I mentioned about the kind of machine, classification of machines. The first one is the uh, simply excited. So this kind of, so we have field and we got armature there. So we have different source for the armature and different source for the field. That's why you call it simply excited DC machine. So we excite, we inject the current here, separate way with the armature circuit. So we need different supply here and different supply here. Okay, that's why we call it the simply excited. And this machine just now I showed, we noticed that it produces very good voltage regulation. This is a shunt where we have this connection between armature and shunt winding connected in parallel. And these are we use to control the field current. So when you control the field, it control the flux. When the flux control, it can be control the voltage induced here. Okay, if the voltage, if the motor, if the motor, you can control the speed. If the generator, you can control the voltage induced there. And this series generator just now, the series winding connected series with the armature circuit. This compound short shunt, where in short shunt we parallel the series winding and the armature, we connect in parallel. That's why we call it short shunt. And in long shunt, we have series winding connected series with the armature. These two machines will give different characteristic, different VI profile, VAIA profile. All right, this okay. Let's skip some part. We can skip there. Okay, we now just basically we go to the separately excited machine. We want to know the basic circuit. So this is a basic circuit for the separately excited circuit. So here we got LF, RFC, RFW. LF stands for the field winding inductance. You know, when you got the coil, inductance coil, then you got LF. And RFC represent the external field resistance used to control the flux there. And then RFD represent the field winding resistance. Because when we got coil, we got resistance. That one we call it RFW. RFW is fixed, constant. But RFC can be used, can be adjustable, because we want to change the flux there, the current. We change the current, we change the flux in the field side. Therefore, the field circuit, for the armature circuit, we have this. RA represent the resistance armature winding. Got armature, got resistance there, RA. And we got the LA, which represent the armature winding resistance. And we got the, this is not LL, this is RL, which represent the external load. Okay, so this is a simple diagram of the DC generator with separately excited kind of connection. Alright, so this we call it dynamic model lah. But when we talk about steady state model, when the steady state, when the current is steady state, then all the inductance here will be short circuit only. So the model become much simpler lah, much simpler, where all the inductance will be short circuit. Then we have this one. Okay, so you can remove the LA and LF from the system. So you can see simple thing now. Right? Okay, so based on this circuit, we can use Kirchhoff law. We can write down the equation for the field side, which is given VF equal to, VF equal to what? RFC plus RFD multiply IF. Kirchhoff law for the field circuit. For the armature circuit here, you can see the equation there. EA equal to IARA plus V terminal. EA also equal to K flux peak that we studied before. And V terminal equal to IARL. And we know that in this particular machine, IA equal to IL. Right? So that's simple equation for the separately excited machine. I hope you can still follow. This is a model for the generator itself lah. Because we need to use this model when we do analysis. We want to study the performance of generator. Definitely we need to use the models. So we use this model for the separately excited machine. Okay, if you plot the characteristic for this machine, Okay, then we can see that this I call it the terminal voltage versus the terminal current. Okay, so just now this is the equation for the generator just now. You see this one, yeah, equation right lah. Yeah, EA equal to IARA plus V terminal. That means V terminal equal to EA minus IARA. Alright, so the red color represents terminal characteristic for the generator. This is a no load condition. No load, no load. So when we increase IA or IT, what happen the voltage terminal, it will go down, The bigger the bigger the current, the lower the voltage at terminals. That the one they call it terminal characteristic lah. The blue color we call it the load characteristic, which is the product between IA RL. We got this line lah. We plot this line. At particular RA, we got different line lah. When you change RA, you got different line. So the intersection between these two lines give the operating point of the generator. Okay. And this is a drop, IA drop. So this you can see the ideal case lah. Without, if the machine has no RA, then you got the dotted line there. But when the IA is bigger, then you can have drop. And then the like that lah. The bigger the IA, the bigger the drop. You can see like that. Or the bigger the current, the bigger the drop. Okay. I hope this is very clear for us to understand the DC generator. Okay, now briefly we go to the armature reaction. What is armature reaction? Alright. So this machine, as we know just now, we have the field winding where we have wound there, wires. So we apply current. So this current will set up flux. We call it flux main in the machine. Or sometimes, as I mentioned before, it's a DQ flux. Sorry, D flux, direct flux, which is north-south pole, or main flux in the system. Okay. And if we plot the flux or the flux density in this particular machine, this is a two-pole machine, north-south pole. So we have this kind of machine. This is north pole, south pole. Simple like that lah. North and south pole. This is a flux density B. And here this armature. Okay, armature circuit without any current flow. So we got this kind of flux produced in this machine. Right, that means your generator is unloaded now. Open circuit. So if we see the flux only due to the main flux without any disturbance. Okay. When your generator is connected to load, right? That means the current will flow. We got current in this armature winding there. Then the current will start to flow. Okay, see dot cross. Dot, that means that this is a dot cross. I mean the current entering, the current coming out there. Okay. Cross means the current entering this armature, and dot means the current outgoing from this armature. So we studied this one. Then this current set up their own flux. How we know this flux line? We just use the right hand rule. By using the right hand rule, we can see the flux line in each conductor, and this resultant flux here it will go up there, towards up. Okay, that's why we call it MMFA lah. MMFA will up there. So this MMFA sometimes we call it the Q axis. So we got D axis, Q axis. So in this DC machine, basically, the flux between D and Q always 90 degree. 90 degree means at any time, at any moment, the machine always produce maximum torque. That's why this machine very, very good in terms of torque production. Torque performance very good compared to the AC machine. And it's not coupled each other. The flux D is not coupled with the flux Q. Flux Q means flux from the armature circuit. That's very good thing. Okay. Never mind. We explained that one already before. So this flux in the machine when the current flow in the armature circuit, or we can say that when we loaded the generator, right? So this flux, basically MMFA, will disturb the flux from the main. Okay, you can see that on the top there. What happened? On the top there, one of the part there, they oppose each other. Here they oppose this flux. Here this oppose the flux. And the other top there, assist each other. This one assist the flux from main. The flux from armature assist the flux main. Flux armature assist flux because the same direction. Okay. Alright. So the impact of this, the impact of disturbance from the flux MMFA to the flux from main, that one we call it the armature reaction. The flux MMFA will disturb the flux from the main pole there. Okay, if you want to go more detail, we can go this side first. we can open this machine. We make it flat like that. So this is north pole, south pole, north south pole. This is carbon brush, carbon brush, carbon brush, and this is a conductor in the armature itself. So by looking this one, we can see that the flux produced by this IA armature current given by this one. Right? You can have this one. It's like picking, and why? Because it deep there, because we got big reluctance there. So it's big reluctance between this and this that cause the drop in the FA. That's why we got sharp drop there, because of distance between carbon brush and the core there is quite big gap, big distance, cause the big reluctance, and you have this drop slip. Okay, and then we can see that lah here. You can see that one side of the pole may saturated because of resultant flux at each other, bigger, for example. So bigger flux cause the saturation happen. Also in this part. If we add these two flux, if we add this flux, original flux here, if this original flux from this magnet, or from this north-south pole, main flux in the machine, with this flux MA, and flux due to IA, you call it MMFA. So what happens if we add these two? Basically, the total flux in the machine will be changed like that. Okay, you can see that. So BA stands for the flux from the armature current. That come from here lah. And BF is flux come from the main field. The resultant here, you add these two, you got the flux between BA plus BF lah. So this will disturb the main flux there. And then some of part will be saturated. Okay, that the resultant. And also they will change the zero flux region shifted. The original is here, now shifted here. So what happened then? It create poor commutation. It will create spark in the machine because the commutation is not so good. Commutation between plus minus. You know that last time I explained already. The current in the rotor itself here is a AC current, whereas the current in the terminal is DC. So when they want to do the rectification process, it's not happen at the same time. It has some lagging time there. That's why they call it the phase shift region. So what happened? It creates spark in the machine, which is not good. Okay, that is impact lah. So what is the impact of what is the main impact? The total flux will be decreased. The total flux in the pole will be decreased because of this impact, because of this MMFA. So which is not good. So armature reaction is actually we don't want that one in the generator, but it exists because of the current flow. Okay, now we go more detail here. So if we plot the graph EA versus IF without armature reaction, we got the red color one. This original flux production. EAIAF IF plot, or you call it the magnetizing curve, original one, without any current in the loop. I mean zero armature reaction lah, because current IA is not flow yet. When the current IA flow, when generator drive load, IA flow, so IA flow, what happen? It create armature reaction. So the total IF actual will drop to IF effective because the drop in flux. The flux original will less because of armature reaction. The current or the flux will be changed from IF to the IF effective by this IFAR. Okay, understand? So now you punya the new voltage will be lesser. Okay, previously got high voltage here, but now become lower. Why? Because the flux reduced due to the armature reaction. The flux per pole is reduced or decreased. That cause the voltage generation will be dropped in the generator terminal. Okay, that's the main cause by the armature reaction. So I'm not sure IF now. So IF basically, IF actual minus IF armature reaction is IF effective. Effective current means that the real current in the machine after we take into account the impact of armature reaction. Okay, drop. That's mean by that. Okay, so this just to show you the plot of the things. So in the machine, basically, first we have IA drop. The bigger the current, the bigger the drop of IRA. Okay. And then on top of that, we have drop due to the armature reaction. This is a load characteristic lah. So now we have our operating point is much lower than before. Here is without anything. This is ideal case lah. On the top here, ideal case. Here because of IRA. And if we take into account the drop due to the armature reaction, we got lower work done induced lagi. So delta VAR ni is drop due to armature reaction. Okay, so that's the impact of the generator when we have armature reaction. So how can we 1 minute lah. Okay, this just to show just now. So I effective equal to IF actual minus IF armature reaction. So how can we reduce this impact IF ni? How can we minimize IFAR ni? How can we make it lower or minimize this impact? We want to reduce the disturbance impact due to armature. How can we do that? Yeah, there are ways to do that. So here we show you how we can do that. The first we can use, you call it the compensating winding and interpole lah. There's two ways can we compensating winding and interpole. So this winding, compensating and interpole winding must be connected in series with the armature circuit. So this your armature circuit, and you must put the compensating winding in series because the current that flow here will proportional to drop in the armature winding. When current increase, the same current increase in the winding. That's why we need to put in series like that. Whatever current change here in the armature side, it will cause the change also in the MMF side there. But the polarity of MMF must be opposed with this MMFA. So the function of compensating winding to compensate the MMFA just now. You got MMFA due to the IA armature current. So we need to cancel this one. So that's why we need to wind the wire here or make it the wire here is opposite thing. That means MMF from the armature reaction will be cancelled by this MMF compensating winding. That's how we work lah. Okay, you can see that here the stator. Though normally the compensating winding we locate at the stator, the surface of the stator pole there. You can see put the wire there, stator pole coming and going, the wire coming and going. And you can see the things there. When this is negative, this is plus. Okay, you can see that this is a dot on the armature current, and the current in the compensating winding must be plus. That's why it generate opposite MMF. So this it will cancel then. So you got MMF here there because of opposite current flow here and here respect to here. So this will cancel each other, and then the total flux will comes from this field winding only. Okay, that's how this is to show you more detail lah, how they manufacture this thing. You can see there's a pole, there's a main pole, and this is your compensating winding. On the top, they make it on the top of the main pole there. And normally this machine, this winding is expensive and used in the large machine only. Okay, the second part I showed just now is interpole. Interpole, we just put small pole between main pole. This is a main pole, north south. In between main pole, we got another pole there. We inject current there, so it become pole lah. Pole north south, and we put the series winding with the armature there. Okay, so why? Because we want to cancel the impact of the MMF due to armature current there. Again, we must wind the wire such that it will cancel the flux from MMFA due to the armature current there. Alright, I think this is very clear explanation for us today. So I think we finished the lecture on the basic principle of the generator there. We talked about previously we talked about the armature winding, and then we have done some calculation on the armature winding itself. And then we go to we also talk about the impact of the armature reaction to the generator and how to remedy, how to solve the problem, how to reduce the impact of the armature reaction. I hope all of you will understand this talk properly, and hopefully see you again in next lecture. Thank you very much for your attention.